welcome to exam question number 1 with me, Robbie Freeman. Let's make a start. This question revolves around these two molecules, which I'll be calling A and B throughout because their actual names are quite long. Speaking of which, so what are they? We'll start with A. Starting with the longest carbon chain, we can see that it's a 6-carbon ring. Looking at this table, that means it's a cyclohexane. The section to the right consists of a carbon triple bonded to a nitrogen, also known as a nitrile group. The left-hand section is the benzene ring or a phenyl group. As the nitrile takes naming priority, we will label the carbon starting here. So 1, 2, 3, 4. This makes it a 4-phenyl cyclohexane nitrile. Right then, now we're done with A, let's move on to B. What even is B? Once again, the longest continuous chain is another ring of 6 carbons. So once again that this means it's a cyclohexane. This time, however, we have a fluorine, or a fluoro group, and a 2-carbon chain, also known as an ethyl group. As the fluorine takes naming priority, we will start there with a 1, and then the ethyl is therefore the 2. Therefore, the full name is 2-ethyl 1-fluorocyclohexane. Phew, I need to sit down. Luckily, here is a chair. Conformation. A chair conformation is a shape that a cyclohexane will adopt rather than flat, as it's more stable. On a chair, there is 2 positions for any member on the ring. There's this one, which is an axial, which means it's going either straight up or straight down below the ring, like an axis on a graph. There's also this one, called an equatorial, as it's on the equator of the ring. For each molecule, there are 2 formations. To work out their abundances, we take a group and call it either axial or equatorial. We then look up a table of values and add the values in. In this instance, the equatorial is more abundant at 95%. This time we're looking at B, and I took the ethyl group and labelled it from there. So the first is equatorial, as it's sticking out the side, and the second is axial, as it's sticking straight up. From this, we can use the reference to find out that the equatorial ethyl group is more abundant with, once again, 95%. Before we continue with parts C and D, I think it's important to go into a bit of detail about what isomers actually are. Speaking very broadly, isomers are simply molecules that share the same formula. They come in 2 main forms, which are structural and stereoisomers. We'll start with structural isomers. Structural isomers are molecules that have the same formula but a different arrangement of the atoms. This means that 2 isomers with the same formula can have vastly different and unique physical properties and behaviors. Stereoisomerism is a slightly different term as it encompasses more than one idea. However, the overarching concept is that the molecules contain the same atoms in the same order but are arranged differently in space. As for stereoisomerism are geometric isomers and optical isomers. Geometric isomerism is also known as cis-trans isomerism, or EZ. This type of isomer occurs when the free rotation of a bond is restricted, most commonly by a double bond. This results in a molecule which either has groups on the same side of the bond or on opposite sides of the bond. If they're on the same side, it is called a cis isomer or Z isomer, and if they are on opposite sides of the bond, they're called trans or E. Optical isomers is where they have the same molecular and structural formulae but are non-superimposable. A common example is your hands. If we imagine that your hands are two molecules, they would have the same formula and the same connectivity, but would show optical isomerism, as when they are superimposed, they do not map onto each other perfectly. As is quite often the case, they are simply mirror images of each other, which can cause molecules to have vastly different properties. To get a better understanding of optical isomers, it's often helpful to see a very bare bones example of an optical isomer around a chiral carbon center. As I mentioned earlier, a chiral carbon is a carbon that is bonded to four different groups. In this example, it's a hydrogen and three fake elements called A, B, and C. The hydrogen will become important for naming, but I'll get to that in a minute. As you can see, these two are mirror images of each other and therefore are non-superimposable. To distinguish between optical isomers, we often have to name them. And to do this, we use the priorities associated with each group. These are known as the CIP priority rules. The hydrogen is there because it almost always acts as the lowest priority group. To name it, we simply put the lowest priority group in the back, in this case the hydrogen, and number the rest in order of a decreasing priority. In our fake example, chemical A is the highest and C is the lowest, but is still above the hydrogen. The left one, therefore, would be clockwise, and the right would be anti-clockwise. In the naming, clockwise is called R, after the Latin rectus for right-handed. The anti-clockwise is called S for sinister, which is the Latin for left-handed. With that idea in mind, let's get back on track with the question. To work out geometric isomers, which we needed for part C, we first need the formula of A, which is C13H15N. A geometric isomer is a type of structural isomer, which means it has the same formula but a different connectivity. We then take this formula that we've worked out and we draw the structures with a double bond that have the same formula as before. I drew these two. Looking at the double bond on the left, the higher priority groups are on the same side of the double bond. This means that it is the Z form of the chemical. The one on the right has them on the opposite sides to form the E isomer of 2-phenyl hept2-enitrile. And finally, for part D, we are doing optical isomers. Optical isomers are different as they have the same formula and the same connectivity, but different arrangements, which means they take up a different space. B has the formula of C8H15F. So for optical isomers, I drew these two. They're both 6-fluoro-3-octenes, however they have a chiral carbon, which means they're open to optical isomerism. We number their groups by priority, with hydrogen taking lowest priority and being sent to the back. We then see whether it's clockwise or anti-clockwise. So on the left we have 1, 2, 3, which means it's clockwise, and on the right we have 1, 2, 3, which means it's anti-clockwise. This means the left-hand isomer is the R isomer and the left-hand one is the S. And that's it. Thank you for watching.